how to close functional coverage using deep reinforcement learning. Okay, so I'll try to give a quick overview of what reinforcement learning is, how to integrate it in a typical test bench as we know it, a modern one, hopefully. And I'll show an example on a design which is an LZW compression encoder, which has a hard functional coverage problem, and see how this agent, this reinforcement learning agent, can help us close functional coverage on this design. Now, the work is mostly inspired from the work of DeepMind, where they try to define an agent to play Atari games at a high level. So if we look at closing functional coverage as a game, hopefully we can get somewhere. And that's what I'm trying to show today. Okay, so we all know that closing functional coverage can be a hard problem, mostly the last percentages, and it's mainly because it's hard to generate the exact scenarios that we want in order to hit the reluctant bins. So we see here how an agent, a DQN agent, I'll talk a bit more about what DQN is, can help us in this context. Okay, so here we see our typical test bench. We have our DUT, stimulus, monitor, checker, golden model, functional coverage. And how do we actually look at test bench as we know it in the context of reinforcement learning? So in reinforcement learning, you have basically two main blocks. You have an agent and you have an environment. So the agent is actually looking at some definition of a state from the environment, which doesn't have to be the DUT state. It can be any state. And the agent, based on this state, generates an action. This action does something on the environment. It changes the state and generates a reward. And based on the reward, the agent tries to understand what's happening in this functional coverage type and try to generate an action that will hopefully close the functional coverage. Now, a bit more concept so that we can understand a bit more. So here I define the functional coverage as the harder the bin to hit, the higher the reward. It's like a game. If you hit like a spaceship high in the screen, you're gonna get a lot of points, and it's the same for functional coverage. If the bins are simple to get, you get a low reward, and if the bins are harder to get, you get a higher reward. And the concept of reinforcement learning agent is to maximize the expected reward, the future reward of a process, of a stimulus process. Okay. Now let's talk a bit about the state. So when I say state, I don't mean the DUT state. I try to emphasize it because I get this question quite often. I focus on a functional coverage type, and my state is a definition of a state that says this is the state that made you arrive at this coverage bins status at the moment. Okay. So an assumption in reinforcement learning is that the state is enough. The state that you give to the agent is enough for the agent to decide the next action. Okay, because reinforcement learning agent is always a Markov decision process, which doesn't need to know about history, but the current set that you give to it. Okay, so in my case, I can keep a history of symbols, sorry, of transactions to the DUT. And the C3 of transaction defines a state at time t. So it's still a Markov decision process. Okay. So in order to appreciate the work of this agent, I took a DUT which is an LZW compressor. Now in LZW compressor, basically you have a sequence of incoming symbols, 4-bit incoming symbols, and they are it's a dictionary-based compression, and they are compressed into 5-bit outputs. And mostly in a LZW compressor, what you will find is a CAM, content addressable memory, which keeps sequences of symbols occurring on the input. And when a sequence occurs here, and instead of outputting the input data, it outputs the CAM address. Okay. So if I have in my case a CAM of 16 addresses from 2 symbols to 17 symbols. Why 2 symbols to 17 symbols? Because the smallest sequence is obviously 2 symbols, and the largest sequence in my case, because I don't want to have like a enormous CAM, is 17 symbols. Now what I want to check, so in total here we have basically 152 locations. Believe me, you don't have to count. And in terms of functional coverage, I have actually 136 bin. Why? Because if a sequence is 2 symbols, this is 1 bin. And here I would have 2nd bin and 3rd bin, and so on and so on. So in total, I will have 136 bins that I need to write to in the CAM. Okay. Now, in order to, if you use a uniform generation of symbols, you will get a really, really bad functional coverage, around 30%. That's something that we're going to talk about later. Now you're asking probably, how can you co-simulate system Verilog and the reinforcement learning agent? So in my case, I use PyTorch in order to code my reinforcement learning agent. And in order for system Verilog to communicate with PyTorch, I use a client-server architecture, where basically the DUT is actually passing the state and the reward to a communication socket, and the PyTorch agent is processing on the fly the state and the reward and generating a new action. Okay, so this is basically the server, and this is my test bench is actually the client. Okay. So this is the deep Q-learning agent. So this is the approximation of the function that actually looks at the state and the reward and generates an action. In the case of DQN, it's what we call an action value function. And the idea in the action value function is that based on the state that I got and the reward that I received, this is the actions that you can take. And for every action, this is the expected reward that you will get if you take this action on the design. Okay? Now you don't have to choose the action that gives you the maximum value for the action value function, because you need what we call in reinforcement learning also some exploration apart from exploitation. When you exploit, you say, okay, this is the action that gives me the highest function, meaning the highest hit in the functional coverage. Then I choose it. But you also want to explore the domain of all the actions that you can take. So sometimes what you do, you insert some randomness and you choose an action completely randomly that will give you probably something that you didn't explore yet. and that gives you a better coverage on the whole actions that you will take once you reach full exploitation. Okay. Sorry. So this is what I do here. This is what we call the epsilon greedy policy that actually sometimes chooses the output of my functional approximation, which is here a 4-layer feed-forward neural network. Obviously, just to get to this architecture will take me another presentation, but it doesn't really matter here. So basically, sometimes I choose the output of the maximum action that will give me the maximum value for my action value function, and sometimes I will choose a random data, and this will be my next action, my next transaction. Okay. So obviously, the beauty of reinforcement learning is not like supervised learning and unsupervised learning, is that the learning is actually on the fly. What I mean by that is when you start your simulation, actually the weights of my neural network are completely random, and at the beginning, the epsilon greedy is on 1, meaning that everything is random from my point of view and is decreasing slowly. And this way, I'm starting to build the weights. The more actions I drive to the DUT, the better the weights are in understanding what is necessary to hit the functional coverage. And once I get to a full exploitation, epsilon greedy, hopefully I want to see that my my functional coverage bins are all hit. Okay. So what you see here is if you take like a uniform distribution of input symbols on our DUT, what we can get in the best case is cover hardly 28 cam write bins, which is equivalent to 44, I think, 44 locations in the cam itself. It's quite expected because in order to get like in order to get quite specific location is hard to, you need to generate a very specific sequence of symbols in the cam. And this is something that obviously uniform generation, as we do generally, wouldn't give you. And that's actually one of the metrics you should consider, for example, if you want to adopt something similar to that, and you use uniform, you build your own test bench and you run a first regression, and you get a very low functional coverage, it means that something is not responding properly to uniform generation. So, so this is probably a good candidate for this approach. And but obviously, if you get like a high functional coverage from the first regression that you do, let's say 85, 90%, probably you don't need this this approach really. I hope that makes sense. And this is actually the DQN simulation results. So in the first, if I run a 500 episode, what I call an episode is actually a state from empty cam to full cam, and it takes me 500 episodes basically to get to mostly all the functional coverage bits, and we see that slowly the DQN agent is learning what's happening and is generating sequences that actually are filling the cam slowly but surely, and I get to almost the maximum. Why almost the maximum? Because I always have this this randomness in the policy. So in my case here, if I run again another episode, the bins that I'm missing here will be filled. So if I merge two simulations, I'm getting using this approach, I'm getting 100% functional coverage using the reinforcement learning agent. Okay, so that's what I say here. In summary, first of all, we identified a design which has a coverage category which is really hard to hit using randomness. So we try to use a machine learning tool that will help us hit the missing functional coverage bins. So what we did, we defined an action value function. And obviously for every action, the expected reward is equivalent to how many complex bins you can hit in the functional coverage. And by using a simple external greedy function, we managed by having 2 simulations to get 100% functional coverage. Yeah, that's it, I think. Right on time. Okay.